start with the last part, fracture mechanical films, thin films and layered structures. As I mentioned, this is really a very large area. I will only try to touch a bit this area in order to show some similarities with the small scale fracture mechanics, where we in principle have looked always to a single material till now, yes? One material, not to really a complex structure or simply layered structure. And why is this more difficult? At first, we have a film material, yes? And this film material can be freestanding, it can be on a substrate, and it can be on an interlayer. So it's the typical things which we have in application. Then this induces constraints in different ways. Then we can have films which are ductile, brittle, and also semi-brittle. Yes? Especially many of the functional material are semi-brittle. The metals usually are ductile, but not always. Then we have our substrate, and our substrate can be stiff, compliant, it can be elastic, it can be linear elastic, non-linear elastic, or it can be elastoplastic. And then we have, in addition, the interface. And the interface, it can be flat, it can be, or it can be structured, and the interface can be strong or weak, or tough and brittle. Strong or weak means if we have no defects, the strength to cause decohesion are high. If weak, the strength to decohesion is low. And tough means if the fracture toughness of the interface is high or it is low, then we call it brittle. So we have here a large variety, and for example also here very compliant are polymers, for example, which can linear elastically deformed up to 5%, or sometimes, yes, 3 to 5%. The films, if they are metals or ceramics, then the ceramics have a fracture strain of few per mil, or if you have metal, then you have a strain of few per mil where plasticity starts. And this makes the consideration of these problems quite difficult, or there are so many different types of cracking phenomena that it would require a few days course. So one of the things what may happen, it is a complete spoiling up of the film, for example. Even when we look to the most simple case, only a film on a substrate. Yes? Then the film may fracture. Then the film may fracture and decohesion may take place, yes, at the interface. Or we will have only a decohesion, yes, such a buckling. You see here few examples. This was I think a chromium layer on a polymer substrate with tension loading. At first, you will see then a video of them. At first, cracks are generated here, and then these buckles generate here, and then these buckles fail. And when we go to the fracture mechanics of these, then we have these differences, and we have this difference in the elastic and plastic properties of these two films. and we have the difference in the Poisson ratio and so on. Then always when we have, especially when we look to the interface fracture, we have always this mixed mode problem. And mixed mode problem itself is a mess to find a simple solution for all types of fracture, for example, for ductile, semi-brittle, or really ideal brittle behavior, because in each case the mode mixity causes different phenomena. Okay. Here you see one example. This is the tension. I think similar, not exactly the same, but we have seen the picture before. But see it here. Yes. So you see here the formation of the cracks. There's a tension loading in this direction. The density of cracks becomes, but the compliant polymer has a contraction in this direction. And this causes then the formation of these buckles, yes? And finally, let us go again. No, let us go back. Let us look again to this. So maybe to see it better. So you see the crack growth, the numbers of crack, the density increases, and finally you have this. And the question is always, are these really, does we have a deboning below, and all these things makes this phenomena quite. The next thing what I want to show is these telephone cord formation, which are often the case when you have a film under compression loading, and the interface strength or the interface toughness is relatively weak. Yes. So when you have this stress, you simply under, you have, in this case, the film is under compression, and what happens is that here you get this formation of this telephone cord. Yes? And fracture mechanic, there is a special consideration of well, you try to understand or determine the fracture resistance simply from the shape of these buckles. Or here you can see another experiment where we have measured, for example, the interface strength simply by a macro test of, well, you have a crack running, and if the interface strength or the interface toughness is significantly smaller than the toughness of the material, then you always get this deflection, and then you can simply calculate the fracture resistance or the delamination fracture toughness of this material, as long as it is a really ideal brittle case. If it is not an ideal brittle case, it becomes really not easy, and it is always then not a single value of the interface toughness, it is then always size dependent. Similar what we have seen before. When plasticity is involved in, then we have a size dependence of these phenomena. If you have an ideal brittle fracture, even this telephone cord formation, the analysis, the fracture mechanic analysis if you can do this in a linear elastic way, then it is in principle possible. The only thing is you have to take into account all the mode mixity effects in this case. And a very good overview is now nearly 20 years old, I think, or more than 20 years old, about this delamination fracture was given by Hutchinson and Su. If you can look here to this. This all these problems, but one have to take into account that these are pure linear elastic consideration. And these are only true if it is really a pure linear elastic behavior. Otherwise, if you apply this, for example, to plastically deformed material, and the values which you obtain are really significantly above the Griffiths toughness, then there is something wrong. Or you have to simply to take into account that then the values which you determine are really size dependent all the time. And it is not simply transferable. In order to measure the interface toughness, there are a lot of fracture mechanics test techniques. These are simple test techniques which are usually used on nearly macro samples. Yes, maybe this will be a silicon a wafer, two silicon wafers put together, a crack inside, or here for shear mode loading. You can then try to realize a changing of the mode mixity, because you always will have a mode mixity, since in very, very seldom the elastic properties of the two materials are quite similar. The plastic properties are for sure. You will never get a system which elastic and plastic similar in such application, I think. Or at least I have never found any example. And so these are the classical macro example, macro test techniques. These are typical micro sample techniques, yes, where you simply try to realize such fracture mechanic experiment by simply edging away, for example, the silicon and moving, then applying a nano indenter and try to measure the strength. But you have always taken into account the difference in the elastic properties between the different material for the strength calculation. And then when a crack can generate, you can also measure the fracture toughness values. And here this would be the mode 1 loading. It is not really mode 1, because in this due to the elastic mismatch, you will always have a mode mixity that is unavoidable. And here, this is a predominantly mode 1 loading, and this is a predominantly mode 2 loading. Or this is also a predominantly mode 1 loading, where you usually apply this here by simply pressure loading. There exist also some fracture mechanic experiments on metallic films, on similar experiments where they introduce here some FIP notches and then try to measure the fracture toughness of thin films. Or other things, very simple techniques, is that they try to peel up the film. They are very simple techniques in industry. They take some stretches, glue it on it, and with glues with different strength, and then look at for which glue strength we get the peeling up of the material, and try to qualify the different type of treatments of the interface toughness. But they are not really quantitative, they are only usually qualitative values for the production. But in principle, one could use, if you really measure then the load, to measure really also the toughness. But what you have to do is, if this is a compliant film, then it is not really a problem. But if you touch a quite strong material and plasticity is involved, then plasticity is then also constrained. In addition, there is a different constraint effect if you have a free surface and only on one side a constraint or on both sides a constraint. If you have a complete peeling up of the film, there is a relative simple consideration, or if you generate here a crack, and if the crack runs then through the film, then it is quite easy to understand this from fracture mechanic point of view. If you have here residual stresses in the film, and the crack runs through the film, then you have a certain energy release rate. And the energy release rate as a function of the crack length is it's very easy to estimate this. It has a linear increase at first with say very short crack length. Then it comes in a steady state, and it remains on the steady state and falling down. And in principle, if you know the length when this peeling takes place, you could also generate the fracture resistance of the interface. But you have really to treat it very accurately. So, as long as we have this, I've already mentioned, as long as we have elastic ideal brittle interface decohesion, this interface problematic can be relatively easily treated, and also all the other fracture phenomena are relatively simple. However, if plasticity develops, then we have to take into account that in most cases the size dependent takes place. For the interface decohesion, this is a result obtained in our group. It was done by Japanese group of Kitamura, and they showed how fatigue crack growth at interfaces, which is a really big problem in the semiconductor industry, and they have shown that the environment in the semi-brittle behavior, even in the ideal brittle case, the environment can significantly affect crack growth. You know that, for example, if you fracture a window glass in a dry air, or if you fracture a window glass into water, the fracture strength is significantly different, because simply the energy which you need to generate the new surface are different, because you have on the other side the water. That's simply a difference. And this also affects strongly the crack growth rate. But in principle, you can draw such curves, but you have often taken into, as long as no significant plasticity in the metallic film takes place, then you can draw this line, or otherwise you have to determine this as a function of the as a function of the film thickness. Or in this case, they are silicon nitride, so they are more or less semi-brittle phenomena. Here you see again similar microsamples for testing. The advantage of such things, what you have seen before, that one can, yesterday I showed you such an example where when we load such a beam, we can measure the strength where decohesion takes place. But it is important that no plasticity should take place, otherwise it will again be size dependent, or here the shear strength can be determined. And when the cracks then generate, then you can measure the toughness, even for these materials. But you have to take into account the difference in the elastic properties and the the multi-axiality of the loading or the mixed mode loading of the crack. Here you see typical arrangement how we test, for example, the fatigue behavior of cracks of metallic films on semiconductor. This is one macro device where we have a silicon film, a silicon sample, and on the silicon sample a metal film. And in order to really realize tension compression loading, we have this relative complex 8-point bending experiment, which really allows fatigue, generate fatigue cracks in the metal films. Another way is, for example, this polyheater test. This was developed by Infineon, where you have simply silicon, then you have a heating device, and then you have here a metal film. It could be aluminum. Typically, it is aluminum or copper. And then one heat up very fast. One can heat up very fast the film. Then we get the different expansion of the aluminum and the silicon. And on one side, we can measure the stresses in the aluminum from the bowing of the silicon, and we can also, by varying this, we can also change the amplitude of the and look to the fatigue behavior, and then we can also introduce cracks and study the crack propagation as a function of the crack length. Here is not plotted the crack length, but in principle this is equal to the crack length times the applied strain and the yield stress of the material. Here different material is plotted. Interesting is that when the crack length increases here from the surface to the and runs to the, this is approximately the end of the metal film, the crack growth rate decreases. This first seems to be a bit strange, but one can understand this is simply a fact that the plasticity in front of the crack is, in the case of full, in principle for the film, it is a full-scale yielding on an elastic substrate, and the crack tip opening displacement decreases when the crack comes to the elastic interface. It is called a shielding simply from the yield stress difference of the two materials. And therefore, we get this decrease in the crack growth. So the consideration of the growth behavior in the thin film is in principle exactly the same what we have seen before in the microsamples. The only difference what we have to take into account that we have a shielding effect simply from the second materials. One of the most important effects in this layered structure, especially when you look to functional material and brittle material, are the residual stresses in these films. And most of the, for many components, the residual stress are really required, otherwise they would not work. For example, many of the hard coatings require high compressive stress in order to do their functions. And the high stresses, they can be generated by thermal treatment or by the growing process, usually. And so the measurements of the residual stress in these micro devices is really a big topic in order to understand the properties of the material, and also when you then try to measure, for example, the interface strength or the toughness of the material, you have to take into account also the residual stresses in the film and the substrate. So for the metallic films, on semiconductors, or also for amorphous films on semiconductors, the stresses in the films are mainly caused by the difference in the thermal expansion coefficient. And here we show a typical effect, what happens in a semiconductor here in the case of the aluminum layer on silicon. If your device during your short pulse is heated up to 400 degrees, which often can occur in power electronic devices, you get the expansion of both things. The yield stress becomes very low, the metallic film is stretched, and then you cool down, the film reduces its length, want to reduce its length significantly more than the silicon, but it is attached to the silicon, and therefore you generate residual stresses. Here, what is this? Oh, this is the yield stress of aluminum as a function of the temperature here of the 500 nanometer film. You can see the yield stress varies strongly with the temperature. It is very high at near room temperature, and it goes down to very small values at or that is, I must look, yes, that's not, must be wrong. Oh, that is the change of the stresses. That's not correct. So first here you can see the yield stress phenomenon as a function of the film thickness, and you have to take into account this very at room temperature, when the film thickness of aluminum, of pure aluminum, which is in the bulk case about 50 megapascal, on the film, on a substrate without a top layer, it is about 100, and it starts with 2 microns with about somewhat more than 100 megapascal. It goes up to 400 megapascal when the film thickness becomes only about 50 nanometer, and can increase even further for thinner films. And this is really important. You see this, for example, if you make so-called wafer curvature test to look to the mechanical response of the strength of the silicon, of the aluminum, and when you have a 50 nanometer film, you are in tension, and then you cool down and you remain elastic. Simply from the bowing you can determine the stress. You get the pure elastic loading of the film. Yes, and you go here in compression at very high stress, and then which determines then the stress in tension. But it always remains nearly linear elastic. It's very small plasticity takes place. But when you have a 1 micron film, a really enormous hysteresis develops during this heating process. You can clearly see this is more or less the yield stress. We have it, you heat up here, the film has nearly no stress, the wafer is striped, then it bends in the opposite direction, and we get the flow stress increase, or the stress increase, then we reach the flow stress. but with increasing temperature, the flow stress decreases, and then the curvature decreases, and when we cool down, the temperature, the stresses changes again, at first elastically, but then it starts the plastic yielding in the opposite direction, and then we get a tension yielding in this case, and exactly the opposite. And this happens in each heating cycle. But when you have this high strength aluminum alloy, then you have nearly the linear elastic behavior. So the technique is quite simple. You have a laser, you have a mirror, then you have a splitting system, then you have different types of, then you have 3 beams, and you have then these 3 beams are depicted on a camera, and if the curvature change, then you have a deviation of the points which you have, and you can simply calculate the stresses. Here you see typical 200 and 600 nanometer films. Typical hysteresis curve is the 200 nanometer has a smaller hysteresis than the 600 nanometer. So you can simply fatigue thin metallic films on silicon, and this is done for a lot of different alloys, and the semiconductor community has really its own material development in order to increase the strength of the material, but also then to the change of the interface strength, which is a second topic in this area. When one has this possibility of microsample machining, then one has another way to determine residual stresses, which are often extremely important, especially in functional material, which are not so easy detectable as for metallic films, and which really can determine the residual stress on extreme small volumes. I will show you here this technique which we have developed about 15 years ago. We call it the iron layer removal technique. What we do is we generate a small bending beam. Here, this is a titanium nitride on silicon, thin silicon substrate. What we have done is, so we have simply machined the way behind, in front of the way. Then we have here a small wall, and then we have removed this material, and then we remove this part of the material. And when we have a residual stress in the film, the beam will be bended. Okay? From the bending of this film, we could determine the mean stress in the film. That's also simple mechanics. Yes. But it doesn't say anything about the distribution of it. It gives only a mean stress. What we then have, so this bending gives us the mean stress. So what we now can do is to remove the material here in a certain section. And what you clearly can see, when we remove the material, then the bending changes. Yes, it is clear, because we remove the material which is under stress. And from the change of the displacement, we can determine the residual stress in the volume which we have removed. It's also not very difficult. In principle, we could use the Stoney formula, but that's not correct in this case, because in the Stoney formula, one has not to take into account the change of the neutral axis due to the residual stresses. But in this case, since the neutral axis really changed with the removing of the material, we have also to take into account this changing of the neutral axis. But from this, we could, this is a a film which is under compression, and this is another film which is under tension. We see exactly the opposite behavior in the curvature. So what we get out is, in principle, a deflection change, and from the deflection change we can determine the curvature in this region, and from the curvature we can then determine the residual stresses by back calculation, and in principle this was where the residual stresses in this titanium nitride film really locally resolved with a resolution of few nanometers. Or here, this is another example for nickel film on, again on silicon. There's nickel film and silicon nitride film on silicon. And so in each of them, we could really determine the residual stresses, and they are usually not homogeneously distributed when the film size is significantly smaller than 1 micron. Then it is usually large differences in the residual stresses, which are often simply a consequence that plasticity takes place, and dislocations on the free surface, they can run out, and on the substrate the dislocations are piled up, and this causes then residual gradients in the residual stresses. And it is not so. If you then try to calculate, for example, interface toughness, you have to take into account this gradient in the residual stress. In addition, that makes this consideration more difficult. And but this technique can also be used to determine 3D distribution of residual stresses. And I will show you here only one example. This was simply to generate residual stresses in the nickel film, which you have seen before. We have simply taken a small scratch on the nickel film with a small ball, and then this was the trace from the small ball which has introduced plasticity in this film. This is now the removed material in front and behind, and here in front and behind the generated wall, and then here this is and now the same technique is now used. What you see here, we simply undercut this bending beam and then remove one after the other. We get the deflections. Undo this again and again, and so you get a large number of deflections for all the cutting processes, and then you can simply calculate the residual stress in each volume element. And so you can really get a 3D picture of the residual stresses. And this is especially for micro-electronic devices, and also for some sensors in the micro dimensions are really important. So they can really vary dramatically in such a case. Okay, that's more or less, that's the advantage of this 3D technique. That's quite big. That's not so big. So I am more or less at the end of my talk. In order to summarize the things, in general, if we have samples with micro dimension, the fracture toughness is only size independent. It is only a material characteristic parameter for ideal brittle failure. And in some case, can be also a material parameter, but then you have to fulfill all the requirements which we have also in macro samples. Yes, fracture process zone must be small compared to the K-dominated zone, or at least it must be small compared to the Hutchinson, Rice, and Rosengreen field. And this is only the case for ultra strong or very strong material, plastically strong material. For weak or for standard structural material, that's usually not the case. The ductility for ductile and semi-brittle material, the fracture resistance becomes size dependent. And this size dependence is, however, really important and not really well examined. Yes, there exist no rules for that, and it is really, I think, in the next few years they will develop all the yes, I would say some simplified estimation of fracture resistance as a function of the sample size. For at least for the ductile material, it is, I think, easier. For the semi-brittle material, I think this will always be a tough case, except, as we have seen for the perlitic steel, that we very near to the ideal brittle case. Then it is again more or less size independent. In fatigue, the behavior will be quite similar as in the case of the toughness, except for the case of the threshold value, because at the threshold, the cyclic crack tip deformation is in the order of the lattice spacing, and since the cyclic plastic deformation is in the order of the lattice spacing, fracture mechanic is in principle, or the fracture process zone is small compared to all the other dimensions, and therefore we can use the fracture mechanic. Maybe we have some problems with the estimation of the plasticity to determine the cyclic crack tip opening displacement, but fracture mechanic at a low crack growth rate should be applicable in the case of fatigue, with some problems. And the last point, if you really want to use the damage tolerance design concept of micro devices, we need these size dependence. With them, I want to thank, and if you have some questions, there were not many questions. You're tired, maybe. And the last part that I often say, yes, especially to, I would say, the new young group of material scientists, but also to the mechanical engineers and especially electrical engineers. Especially the electrical engineers, they think fracture mechanics is extremely difficult. Yes, they cannot understand what happens there. Yes, but also the young material scientists often come to a similar conclusion that fracture mechanics is really difficult. But fracture mechanics is not so difficult. What is really difficult is the fracture behavior of our material. And that's really the difficult thing, yes. When all the time, when we come to the difficulties, then we have to look, oh, that's for this, the fracture process zone becomes so large. And it is not clear what is crack propagation when we have first maybe a small amount of blunting, then we have a formation of micro cracks, then the micro cracks coalescence with the main crack. How should we characterize it? Yes, yes, we can characterize. If we have, for example, small-scale yielding condition, then we can say, okay, at this K happens this. We have an R-curve behavior, for example, for the fracture resistance. Why the material have these? This is a material problem and not a fracture mechanic problem. And so the fracture mechanic, to my opinion, yes, is not so difficult. What is really difficult is the fracture behavior, and it will be never solved completely because we will always develop new materials and there will occur new fracture phenomena. Okay, with them, I will close really.